Hello, and welcome to part 2 of the lesson on section 12.10, Taylor and Maclaurin series. In this lesson, we'll look at the graphs of Taylor polynomials and their relationship to the graph of the function they approximate. We'll also derive a Maclaurin series for some other functions using the ones we already know. Let's look at the sequence of partial sums for a Taylor series. Each term of this series is denoted as capital T with subscript indicating the degree of the polynomial. Let's use the Maclaurin series for e to the x. Remember that the terms of this series are x to the n over n factorial. So t sub 0 equals 1. T sub 1 is 1 plus x. This is called a first-degree Taylor polynomial. T sub 2 is 1 plus x squared over 2. This is called a second-degree Taylor polynomial. Now I'll compare the graph of each Taylor polynomial to the graph of y equals e to the x. T sub 0 is only a good approximation of e to the x, very close to x equals 0. T sub 1 sticks close to e to the x for a slightly longer period of time. T sub 2 is very close to e to the x for a longer interval. And T sub 3 curves closely to the graph of e to the x for an even longer interval. As we add more terms to the end of the polynomial, the graph is a close approximation to the graph of e to the x for longer intervals. The numbering of these examples is continued from the video for part 1 of this lesson. In part 1, we looked at example 1, so now we're on example 2. Here, I'll evaluate the integral of the sine of x to the third as a power series. You'll need to memorize the power series for the sine of x. It's an alternating series with only the odd-numbered powers and factorials. As an aside, I should mention that the third and fourth degree Taylor polynomials would be the same for this series because the fourth degree term is 0. Along the same lines, the fifth and sixth degree Taylor polynomials for the sine of x would both consist of the first three terms you see on the screen because the sixth degree term is 0. And so on. I'll substitute x to the third for x, and then I'll integrate term by term. So as a power series, the integral of the sine of x cubed is x to the fourth over 4 minus x to the 10th over 60 plus x to the 16th over 1,920 minus x to the 22nd over 110,880, and so on. Next, I'll use the series we just found to estimate the value of the integral of the sine of x to the third from 0 to 1, correct to within 0.001. Evaluating from 0 to 1 results in the series 1/4 minus 1/60th plus 1 over 1920 minus 1 over 110,880, and so on. Since this is an alternating series, the error in using the sum of the first n terms to calculate the sum of the entire series will be less than or equal to the value of the n plus first term. Using a calculator, I find that the first term that is less than 0.001 is 1 over 1,920. So by the alternating series error estimation, the sum of the first two terms of the series should result in an answer that is within 1,000th of the exact sum. Let's check that. Using the integral function on my calculator, I find the integral of the sine of x to the third from 0 to 1, and that's about 0.233845. The sum of the first two terms of the series is 7 over 30. And the difference between these two answers is about 5 times 10 to the negative 4, which is less than 0.001. This concludes part 2 of the lesson on section 12.10, Taylor and Maclaurin series.